shows two main types of existence of salt. It shows us two main existence of salt in the world. The left side is the pure highlight, and it was undeformed of very high purity, and the left side is the deformed and fractured salt that is more often we seen in the salt formation. And so, first of all, I'd like to mention our motivation of the study of salt. As more and more attention attached to the pre-salt and sub-salt imaging, especially in Gulf of Mexico area, and some companies, they have already been played the dirty salt technique to the salt formation. We'd like to know actually more precise about the salt properties. So that comes to the main content of my talk today. So there are mainly two parts. The first part is the log measurement. We studied the salt, the situation that salt could show seismic anisotropy in this the sample scale, and we studied the pure salt. We studied the deformed and impure salt, and we have the detailed measurement of them, and it shows the anisotropy parameters for some salt. And the second part is we studied the log value of the the salt in the Gulf of Mexico area in the field scale. In this study, we have more information about the salt velocities. So we generate the empirical relationship of the salt velocity with depth and density, and that should provide some reference for the subsalt and pre-salt image, the velocity model, especially for Gulf of Mexico area. So so let's see our lab measurement first. The most beautiful results come from our pure highlight. Basically, the pure highlight, it belongs to the cubic symmetry anisotropy class. Our measurements consistent with the theory that it shows a constant velocity of P and show wave in three symmetry axes, and it shows the show wave splitting on other directions. The results of as the first arrivals of show wave splitting we're showing here is when we have the show wave propagating in the halfway between two symmetry axes. So we can see from this first arrival in the respective of 0 to 360 polarization, the show wave splitting is very prominent here, and we have over 18% of the show wave velocity splitting here. If you're interested in how we conduct this the measurement, we can talk after the presentation. But generally, I'm showing the result here. For these symmetries, the velocities of three symmetries consistent for both P and show wave, and we have very prominent show wave splitting in the halfway between two symmetries. And we also came up with the anisotropy parameters. So we did our computation of the phase velocities based on our parameters we calculated from the measurement. This is the velocity distribution in the symmetry planes in 4 quadrants, and we're not the first one who did these things. The right side is the previous results from Zong 1995. They have the similar results as us. So this is the phase velocity surface. So outside is the largest velocity is the P wave, and it varies a little bit in all horizon view, and the variance of the P wave is 7% maximum, and the show wave it shows splitting in the direction other than the symmetries. So the right side, the left side is our results. We put our results together. So the soft lines are ours and the dotted lines are theirs. So they match very well and also consistent with the theory. So our first arrival with the show wave slitting that we show in the last slide is carried out in this direction. We can see the dominant show wave slitting in this direction, as well as the slowest P wave. And basically, this is our cubic symmetry, and for more measurements are carried out for the fractured, also deformed salt samples in Gulf of Mexico. This is actually in Hockley. This is more complicated than the cubic one, and we can see from the sample that under the line it shows some preferred fractures. This is another scenario that we expect to see seismic anisotropy. That is, if we have dominant stresses in this area and some preferred fractures, we could see the show of splitting as well as P wave variation in different directions. But from our current measurement, we cannot conclude exactly symmetry axis for our fractured sample. But basically, we can see from the three directions that we have biggest variation on X and Y. They're close, relatively close to each other, and little and a smaller variation in Z direction, and also a faster velocity in Z direction. That one gets for this variation could be that we have our fractures oriented more vertically in this way, but we do not generate precise anisotropy parameters for this one. And I'd like to show another sample that doesn't show that much anisotropy parameters. This is a core from also Hockley. It has the same depth as the previous one, but a different location. So it's taken from a horizontal well, and it is more isotropic compared to the previous one, and it doesn't show much show of splitting. So based on our measurements for different samples, we can conclude two main scenarios that could we expect the seismic anisotropy. The first one is the area with large pure salt formation, that we could expect the cubic symmetry in this area. Actually, we have some basins that have very pure salt basins, as we measured in the first one, the North Wilson Basin, the Michigan Basin, and some others. And another scenario that we expect the anisotropy is for the fractured, and they have the area that have dominant stresses. We can see the very big velocity variation in this area. But for other areas, we still need to study on the isotropic properties. This is one numerical model that we did for the quantification of how much difference the cubic could make to the travel time difference. We upscale the model. It's a 3D model. It's just a single layer, and we first calculate the travel times with the isotropic features, and then we substitute that with the cubic symmetry. The parameters we calculated from our measurement, and we subtract the travel time to get this difference. The maximum difference we expect is also from the halfway between two symmetries, and for the 1 kilometer thickness, the travel time difference one way P wave could up to 20 milliseconds, and we did also other numerical models of show waves. If you're interested, we can discuss later, and just give the impression that how much difference this cubic could make. And actually, the 1 kilometer thickness is very realistic, because we expect, because there are a lot of salt basins that is over 3 kilometers in Brazil. So the 1 kilometer is realistic. So let's go to our second part. We are lucky to get a lot of data from Dr. Huffman that in the Grand Gulf of Mexico area, we have 142 wells and that drill through the salt. So basically, it covers most area in Upper Gulf of Mexico area, and the coverage is up to near 100,000 square kilometers. So based on this data, we did a statistic study and to generate the empirical velocity, the empirical relationship between the salt velocity and the depth and also the density. We believe our results are representative, especially for Gulf of Mexico area. Also, it will provide more realistic velocity model for the imaging compared to the measurement in the lab. So this is our results for the velocity relationship with depth. So basically, we can see that different from what we imagined before. The velocity does show the trend with depth. It's just, although the increment is not that significant, but it's definitely not a constant velocity. So we did the least square curve fitting for this trend, and we came up with a relationship. And also the standard deviation is shown in the lower plot. So in terms of kilometers per second for velocity and kilometers for the depth, we have the slope of 0.13, and basically the main velocity for the whole section is around actually 4.5. So this is our prediction for the relationship, and we did one more prediction from our relationship of the depth to pressure. We generally just use simple relationship with the depth and the pressure. Then we have another relationship for generally for the pressure. So we correlate our results from other people's work and to see if they're consistent or not. So the first one we're showing here is actually the lab measurement for the salt that under pressure. So our curve, our prediction is the blue line here. It fits well with the their measurement of the P wave under 70 degrees. Actually, because most of our data are centered in 3 kilometers to 4 kilometers depth. So if we convert that to the temperature, that is almost like 100 degrees. So that is reliable for their measurement for the 70 degree. Another comparison is this different from the previous lab measurement. This is the real field data. This is the basin in Russia, and they got this range of the salt velocity variation with pressure. So our prediction fit their upper bound here. So this fit actually suggests support our prediction with depth in the other way. So this is our result with the velocity and the density. Basically, it doesn't show very good correlation as the previous one, but it's more scattering. Most of the density is around 2.06, and we further plot our density to Gardner's and find that our plot fit exactly with his prediction. But we cannot generate like any relationship valid for this density. But we can think about it with the velocity varies such a big range at the same depth. The one possible reason could be the anisotropy. It's just the one case. We still need like for the study of this. So let's go to the conclusion. Basically, we did the two-part of our talk. The two-part of our study, the study in which case we expect the salt anisotropy. The first one we said it is for the pure salt, and the other one is for the stress zone. And we need to be very careful when we're doing the velocity models in these two areas. And also we provide the empirical relationship of the velocity over depth, and also not valid, no valid relationship with the velocity and the density. So in this case, we could provide reference for the step-salt image, step-salt pre-salt imaging. So salt has got a lot of good stuff to do, so we need to keep studying on the salt. We'd like to give our especially thanks to Dr. Fred Hildman. Hope we didn't mess up too much with your data. And we'd like to thank all the AGL personnel, all the sponsors, and thanks for all coming.